Now that you've had a chance to work on some circuits and trails on the activities, we are going to talk specifically about Eulerian circuits and Eulerian trails. First thing we're going to do is review the definitions of trails and circuits. We're going to use those definitions to help us define Eulerian trails and Eulerian circuits. And then we're going to make a conjecture about when an Eulerian circuit or an Eulerian trail exists in a graph. And then we're going to prove part of that conjecture, but not all of it. So let's talk about some of the special walks that we looked at in the last video. If G is a graph, we say a trail in G is a walk in which every edge appears at most once in the trail. And a circuit is a trail, so every edge appears at most once, but it's special because it begins and ends at the same vertex. And then on top of this, we have some special trails and special circuits within the graph, which sometimes exist and sometimes do not exist. So let G be a graph. We say an Eulerian trail is a trail that is not only a trail, but it includes every edge of the graph. A trail in general does not have to include every edge. An Eulerian trail does. And an Eulerian circuit is defined similarly. It is a circuit that includes every edge of the graph. So whenever we put Eulerian in front of something, it means every edge of the graph is included. All right, so let's look at this particular graph and see if we can come up with either an Eulerian circuit or an Eulerian trail, or actually in this case both. And it turns out it has an Eulerian circuit, E, A, C, D, A, B, F, C, E. And to show you that it is indeed an Eulerian circuit, we're going to go ahead and first of all notice that it begins and ends at the same vertex E. So it is at least a closed walk. And now let's see if it's a circuit. See if, first of all, every edge gets used, and second of all, that no edge gets used more than once. So we start on E. There's our blue one. And then we're going to move on along. So E to A to C, then over to D, and then back to A. And notice that even though we're hitting A for the second time, we've only used the edges once. Now we're going to move over to B, move over to F, move over to C, and then again C got hit twice, but still all the edges only got hit once, and then back to E. And you can see that we didn't have to change the color of any of the edges. Right? That means they were used only once, and all the edges are red, which means all the edges were used. So that is an Eulerian circuit. It is also actually an Eulerian trail. Remember, an Eulerian trail only demands that every edge gets used once. That was certainly true here. All the edges were used. It is a trail, right? A circuit is a special type of trail, so it is an Eulerian trail. So we got an Eulerian trail and an Eulerian circuit all in one fell swoop. All right, so now we're going to look at this graph. It's a slightly different one. And we're going to find an Eulerian trail that is not a circuit. And here I listed the vertices A, C, D, A, B, E, D, F, E. You can see that it begins at A and ends at E, so it's not going to be a circuit. We just got to make sure that it hits every edge, and every edge gets used just once. So we're going to start at A. We're going to move down to C, then over to D, and back to A. So A got hit twice, but all the edges involved so far have only been used once. Now we're going to move over to B, move down to E. Let me see, we're going to move over to D, then over to F, and then back to E. And notice that every edge got used exactly one time. The vertices A, D, and E got used twice. We began at one vertex A, ended at a different vertex E. That's an Eulerian trail, but not a circuit. And it is not perhaps obvious, but this particular graph does not have any Eulerian circuits. So we found an Eulerian trail that is not a circuit, and it turns out also that it has no Eulerian circuits, which may lead you to wonder, is it possible for a graph to have both an Eulerian trail that is not a circuit and an Eulerian trail that is a circuit? And the answer turns out, no, you can't. And in fact, based upon what the examples here, perhaps, and certainly the examples that you looked at in the in the set of in-class activities where you were actually looking for Eulerian trails and Eulerian circuits, you probably came up with the following guess. So if G is a connected graph, and remember, it has to be connected to have any kind of Eulerian trail because we got to make sure to get to all the vertices. G has an Eulerian circuit if and only if every vertex of G has even degree. So you need even degree on every vertex to have an Eulerian circuit, and it turns out that having an even degree at every vertex is precisely what we need for an Eulerian circuit. That's the if and only if part. And this one's a little more sneaky. G has an Eulerian trail that is not a circuit if and only if exactly two vertices of G have odd degree. And what that means is, other than those two that have odd degree, the rest have to have even degree. So you can't have two vertices that have odd degree and then another one that has odd degree. Exactly two vertices of odd degree, and then the rest have even degree. So what we're going to do is we're not going to prove this theorem altogether. You're going to prove half of each theorem, and in this video, I'm going to prove the other half of each theorem. So let's see what we got. So we're going to do a partial proof of one. And remember, it's an if and only if statement, so we have actually two proofs. We assume the first one and then show the second one. Then we assume the second one and show the first one. What we're going to do on this first one is we're going to assume that G has an Eulerian circuit, and then we're going to show that every vertex in the graph has even degree. All right, so we're going to do this using an algorithm for figuring out how to figure out how the edges work. But we know that G has an Eulerian circuit, right? That's by assumption. And we're just going to say, let's assume that that Eulerian circuit looks like the following. V1, V2, all the way to Vn, and back to V1. And I do want to note that some of those V's in that sequence of vertices could very well be the same, but none of the edges can be the same. And since it's an Eulerian circuit, it has to include all the edges in G, right? So Vi plus 1, each vertex and the one right next to it, those are going to be edges. And if you put all those edges together, you get all the edges in G. All right, so let's look at a random vertex of G. So we know that that Eulerian circuit has all the edges in the graph. But if it has all the edges, that means it has to include all the vertices as well, right? Each of the edges has a vertex attached to it. It's got to have all the vertices in the graph. That means our V that we're looking at, our random V that's a vertex of G, it's one of those VIs. And in fact, we can actually assume without any loss of generality that V is equal to V1, because if we have an Eulerian circuit, we can actually start that circuit on any vertex. So for instance, if the V actually isn't V1, it's some other VI, what we can do to make an Eulerian circuit that begins at VI is we can just shift the order of the vertices. We can start at VI, go to VI plus 1, all the way up to Vn. We can go right back to V1 because that's the beginning of the back to the beginning of our original Eulerian circuit, and then go all the way out to Vi, and that gives us an Eulerian circuit. So since we can start at any vertex for an Eulerian circuit, we might as well, we can say without any loss of generality that V is actually equal to V1. So the first thing we're going to do when we go on our Eulerian circuit is we're going to leave V. Now, we have to leave V along an edge. So that's one edge that we've already traveled on that V is incident to. Now, that cannot be the only edge that V is incident to, because since V is the first vertex in our Eulerian circuit, it has to be the last one as well. That means we have to come back to it sometime, right? At some point, we have to return to V. And we have to return to V along a different edge than the original one because we can't use any edge more than once. So that's two edges we have so far. Now, that could be the end, right? We return to V and we're done with the circuit. And we have a degree 2, which is even. But it is, of course, possible that we have more edges coming out of V, and we have to use them because you have to use all the edges in our Eulerian circuit. So we might travel out of V again. That becomes 3 edges. But since we end on V, we always have to come back for a 4th edge. So the basic idea here is every time we leave V on our Eulerian circuit, along one of the edges, we have to return along another edge, and each time we leave and return, those edges are different from all the other ones where we left and returned. And since we have to end on v, the last one we're going to get is a return edge. What that means is that the number of leave edges is exactly the same as the number of return edges, and those are all the edges coming out of v, which means when we add those edges together, we get the degree of v. And since they're the same number on each one, that tells us that we have an even number of edges that we've traveled on. And since all the edges are traveled on for our Eulerian circuit, that means v is incident to an even number of edges, and that tells us that the degree is even. Because remember, there's two ways we can think of the degree. It is the number of vertices that v is adjacent to, or it is the number of edges that v is incident to. Since we have an even number of edges that v is incident to, has even degree. All right, so we're going to do the same thing with part 2. We're just going to prove part of it. We're going to prove the part where we assume that G has an Eulerian trail, very similar to the last one, and we're going to show, and we're going to assume that Eulerian trail is not a circuit, and we're going to show that exactly 2 vertices have odd degree, all the other ones have even degree. So G has an Eulerian trail, V1, V2, all the way out to Vn. Each of the vertices that's sitting right next to each other, those are edges, and collectively in that Eulerian trail, you get all the edges of G. And the last thing that is true is V1 and Vn are different vertices. Okay? And as you've seen through the examples, you're probably guessing that the 2 vertices that have odd degree are the first one V1 and the last one Vn, and all the other vertices are the ones that have even degree, and you would be correct. So that's actually going to help us out with the proof. Because now we're going to do 2 cases, right? We're first going to look at the VIs that are not at the beginning and not at the end. So the ones between V2 and Vn minus 1. And again, our guesses for those is they're going to have even degree, right? And so we're going to try to actually prove they have even degree. So during our Eulerian trail, starting at V1, the first time we get to Vi is by entering it along an edge. Remember, it is not at the beginning of the Eulerian trail, so we could not have got started there. So the only way we can get to that vertex, which we have to, is by entering it along an edge. So that's one edge that we've traveled on so far, coming into Vi. But we know that it is not the last vertex, it's not the ending vertex, that's Vn. So that means when we enter Vi, we have to leave it again. And that gives us 2 edges traveled on. Now, it's very possible that that is the last time we ever encounter Vi, and we have degree 2. However, it is possible that we come back and visit again. But when we visit again for the 3rd time, we have to leave again because we can't end at Vi. We always end at Vn. So that gives us 4 vertices. And in fact, if we continue this process, every time we enter that vertex along an edge, it's got to be new. And then every time we leave, we got to leave along a new edge. So once again, we're in a situation where the number of enter edges equals the number of leave edges. And since it is an Eulerian trail, that is all the edges, which means that Vi has even degree. And that is true for any vertex that is not V1 and is not Vn. All right, so let's now look at the other 2, V1 and Vn, and we got to show that those 2 have odd degree. So let's look at V1 first. Now, at the beginning of our Eulerian trail, we leave V1 along an edge, and if we're counting, that is 1 edge that we've traveled on. Now, that may be the last time we encounter V1, in which case we have a degree of 1, which is odd. But it's also possible that we can come back to V1 again, that's 2 edges. But we can't stop there because it's not an Eulerian circuit. So we'd have to leave again, and that would give us a 3rd edge, which is also odd. And we get again into this pattern where every time we enter V1, we have to leave because we can't end the Eulerian trail on V1. Which means that if we look at the number of leave edges, we have 1 more leave edge than we have return edges. We have that 1 leave edge at the beginning, and then after that, the return edges and the leave edges have to be equal. So that return edges or leave edges are equal except for that first one where we left V1, which means the number of leave edges equals the number of return edges plus 1, and those are all the edges coming out of V1. So if we add those together, we get twice the number of leave edges plus 1, which is an odd number, so V1 has odd degree. And then we can play a similar game with Vn. The first time we encounter Vn is on a return edge, an entering edge. right? And then every time we leave, we have to return again because Vn is going to be the last vertex in the Eulerian trail. So the end of the Eulerian trail ends on Vn, so every time we leave Vn, we got to come back. And then we have a situation where, where the number of return edges is equal to is one more than the number of leave edges. Again, we get an odd degree for Vn, so V1 and Vn both have odd degree, and that proves the theorem. All right, sorry for that premature flip to the last slide. So now that you kind of understand how those go, we're going to look for some activities on the file called Eulerian circuit algorithm, and that is going to give you an idea of how to find an Eulerian circuit when all you know about the vertices is that each one has an even degree.